All right, let's just jump right into it. We all learn this one law in school, right? The one that seems totally, completely unbreakable. But what if the biggest stage of all, the entire universe, is playing by a different set of rules? What if Einstein himself pointed out a cosmic loophole that changes, well, everything we thought we knew about energy? I know, it sounds kind of crazy, doesn't it? But when you really look at how cosmologists talk about our universe, you're left with this one nagging question. Did hundreds of the smartest people on the planet just forget one of the most basic rules of science? Or is there something much, much deeper going on here? Okay, so first, let's refresh our memory. This is the law we all know and love. It's fundamental. The idea is that in any closed system, the total amount of energy is always the same. You can move it around, change it from potential to kinetic, from chemical to heat, but the grand total never, ever changes. It's like the universe's most reliable accounting rule. And we see this rule working absolutely everywhere. It's the reason perpetual motion machines are impossible. It's the bedrock of chemistry, of engineering, of our entire understanding of how the world works. It just seems solid, unbreakable. But then, well, then we started looking at the cosmos on the grandest scale. And here's our culprit, the thing that messes up all our neat and tidy books: dark energy. You've probably heard of it. It's that mysterious force that's making the universe expand faster and faster. And when you look at how it behaves, you stumble into a massive paradox. So here's where it gets really weird. As the universe gets bigger, the volume of space goes up. Obviously, right? But the strange thing about dark energy is that its density, the amount of it packed into any given chunk of space, seems to stay completely constant. So, if you have more and more space, and the amount of energy in each bit of space is the same, well, the total amount of dark energy in the universe has to be going up. Energy is being created out of absolutely nowhere. If you're sitting there thinking, wait a minute, that can't be right. Good, you're thinking like a physicist. It feels like a massive, glaring violation of the rule we just talked about. And as cosmologist Sean Carroll points out, you're not alone in feeling that way. It feels fundamentally wrong. So what gives? The whole key to this puzzle is that the law of energy conservation isn't wrong, it just comes with a hidden condition. It's like there's some fine print, an asterisk we never got told about in high school physics. And that little condition holds true for everything on Earth, but for the universe as a whole, not so much. This is the huge mental shift we have to make. You know, in the old Newtonian way of thinking, space-time was just the background, a fixed, boring stage where the play of physics happened. But Einstein's view is completely different. In his universe, space-time isn't the stage. It's one of the main actors. It's dynamic. It can stretch, it can bend, it can evolve. And that right there is the fine print. That ironclad law we learned, it only works perfectly when the background, that stage, is fixed and unchanging. But our universe isn't static. It's expanding. The stage itself is changing, and that changes the rules. And here is the mind-bending result of all this. In general relativity, because space-time is an active player, it can actually give energy to things or take energy away. The total energy of all the stuff in the universe doesn't have to stay constant because the universe itself isn't constant. It's not that energy comes from nothing. It's that space-time itself can change the total. Now, it's really important to get this. It's not a one-way street. It's not just about creating energy out of thin air. Space-time is an equal opportunity player. It can give energy, but it can also take it away. Think of it like a cosmic transaction. On one side of the ledger, you've got dark energy, where the total energy is going up as space expands. But on the other side of the ledger, you have something like light. And for light, the exact opposite happens. Imagine a little particle of light, a photon, zipping across the universe. As space itself expands, that photon's wavelength gets stretched out right along with it. And a longer wavelength means a lower frequency, which in physics means less energy. That photon literally loses energy as it travels, and that energy, it just vanishes. We call this cosmological redshift. And look, this is not just some wild theory. The energy loss from redshifting light is a rock-solid, verified prediction of general relativity. It's been happening for 13.8 billion years. In fact, our models of the early universe, the ones that perfectly predict how much hydrogen and helium were created right after the Big Bang, they absolutely depend on this energy loss being real. So on a cosmic scale, energy is not conserved. Okay, so if the science is settled, what's all the fuss about? Why do people still argue about this? Well, all the physicists agree on the math. They agree on what we see. The real debate is just an issue of translation. It's about finding the best words to explain this totally bizarre reality to the rest of us. And believe me, this is not a new argument. The debate's been going on for over a century, literally since the day general relativity was born. You had giants like Einstein and Noether arguing over what energy conservation even meant anymore. Decades later, you had Erwin Schrödinger calling one of Einstein's mathematical tools for this a sham tensor, which is about as big an insult as you can get in physics. Today's debate is just the latest chapter. So really, it boils down to two main camps. In Camp 1, you have the plain truth. These are the folks who say, let's just be honest about it. Energy isn't conserved in an expanding universe. Space-time changes, so energy changes. Simple. In Camp 2, you have the complicated fix. These guys try to save the old law by sort of redefining what total energy means to include the tricky idea of the energy of gravity itself. But, oh man, this fix gets messy. Fast. When you try to count the energy of gravity, you run into all sorts of problems. The number you calculate can actually change depending on your point of view, which is a huge red flag in physics. You end up having to talk about things like negative energy just to make the books balance. It relies on these mathematical tools that, as we saw, even Schrödinger thought were kind of a sham. And that brings us back to this really simple, powerful idea from Sean Carroll. Maybe this simplest explanation is just the best one. Instead of twisting ourselves into knots trying to save an old law, maybe we should just embrace the incredible reality that Einstein showed us. Space-time is alive, and because it changes, the total energy inside it can change too. It's a broken law, but it reveals a much deeper and honestly a way more interesting truth about the universe we live in.